All right, so I'm going to teach you combinatorics on words. So welcome to this lecture. Thanks for showing up. And it is the first time I teach here in the Higher School of Economics, so I'm not familiar with your background yet. Therefore, your questions and comments are very welcome for the whole lecture, if something is too hard, too easy, too slow, etc. In particular, if I write down a statement or a theorem on the board and you see how to prove it, or even you have just ideas how it could work, don't hesitate to raise your hand and tell me instead of just waiting for me to write proofs or something. So first I should tell you what is combinatorics on words and why it would be interesting to study it. So just I need a few definitions, but I guess everybody know what a finite words is because it's just a character string in a sense you're used to in programming. You've all done a bit of programming at some point, and you probably all use the language with the notion of character string. This is exactly what we're going to study. So I will be a bit more formal than just programming, so I will start with an alphabet, so it's a finite set of letters. Alphabet. Of course, it should be non-empty and so on. And so I denote by sigma star the set of all finite word over sigma. And if I have a finite word, so character string W, I denote the absolute value of W, its length. The individual letters, so W. Sorry, it's a string of definitions at the beginning, so just I can start stating interesting things. So if I have a word of length n, I call W0, W1, Wn minus 1 the individual letters in the word. And if I have another word, U of length m, I will denote the concatenation of W and U, something that you all done at some point, by concatenating U and W. So this means that basically this is equal to W0, Wn minus 1. So here I've written on the board just a couple of very easy notations. I have words, I have concatenation, I have length. And the question I ask is, well, basically what can we say, what can we do as a mathematical theory just with this? This is our starting point, and what interesting things can we say essentially about concatenation actually? This is the only operation here that we're going to deal with. The length is something obvious. And so why bother? Why would you ask yourself questions about concatenations? Well, probably you have in mind text, because I said character string, so usually the obvious interpretation is text. So if you have some kind of text, you might want to perform algorithmics, say string matching, you want to find a substring inside a big string, something like this. You want these algorithms to be efficient, so you need to understand something on the structure of the words, and it's usually a good idea to study the object by itself, like to study its properties, and then say, okay, now I have this or this property that is valid on any finite word, on any string, I can invent an algorithm that's good for it. So that's the text interpretation. But you could do other things with exactly the same formalism. Here, I use the term word. I don't use programming notation or programming vocabulary for that matter. And that's because it's actually a very general theory. It started, as I mentioned while you were sitting down, as a language theory. The first people looking a bit into this were linguists, actually, trying to understand, for instance, things like if you have an S at the end of an English word, probably it is a noun in the plural, like I have dogs or instead of dog. It could be a verb to the third person, like he does or something like this. And so they asked themselves questions about words to actually understand the structure of language. So we're not going to do that too much, but it's also one of the motivation, which is more historical, not that trendy today. All right, you can also, you have many things you could imagine. If you're interested in parsing, you're writing a compiler, or you have some software parsing a configuration file. You want also probably to understand this, but I guess you got automata theory already? Yeah. Okay, so basically we're in lower level. This is low level. If you're doing C with automata, we're doing assembly language here, basically. But there are more surprising things, like if you're doing algebra, just plain abstract algebra, you can see your words are products of variables. If I write something like, if I give myself an alphabet, say A, B, where you imagine they are variables, then you can write equations on this. I don't know, you could consider this not exactly as a text, but as a product of formal objects in any monoid. So basically all the results you can say about concatenations, you can use them for text. You can also use them for algebra. And that's actually going to be the most interesting part of the first hour. I'm going to show you, we're going to do algebra in this very simple and general monoid, and we'll see that, okay, you can say interesting things about text, and on the contrary, sometimes text analysis could say interesting things about algebra, even if it's less common. All right, so since I mentioned monoids, everybody is clear with what a monoid is. As I told you, I have no, I could recall quickly. Operation which is and exists a neutral element. Yes, all right. So about that neutral element, I will write epsilon, the unique word that I could write like this. So maybe it's more helpful if I give you, it's the word of length 0. And of course, it is a neutral element for concatenation. If you add 0 letters, you get nothing. And so indeed, what I say when I explain you that this structure is a monoid, I mean that concatenation is associative, that it has a neutral element, which I note epsilon, which is the empty word. But it's not necessarily commutative. In general, you have no reason, if you have two words, you have no reason to have this equation here. Just pick X a letter and B another letter. In our formalism, AB is different of BA. One last thing, and then I start asking you questions. So I defined concatenation. I said we're in an algebraic context. It will be useful to define also, if I have some word U, I can define U to the power 0 to be the empty word, and U to the power n plus 1 being UNU. Just if I raise a word to some power, it just means that it concatenate with itself. So AB, this would be AB to the cube. And I should write that this means, oh, and okay, associativity. UVW like this is equals to UVW like this. So I will never write this parenthesis, and we will concatenate things freely. Okay. And so, in general, I was saying this equation has no reason to be true if you pick any arbitrary word x and y. But could you invent examples where it is indeed true? Because we can, in some specific cases, we might have commutation between two elements. It's a palindrome?
Alphabet of size 1.
F what?
Alphabet of size 1.
Alphabet of size 1, okay. Yeah, okay, so let's take another. Palindrome, who should be a palindrome? X, Y, both?
It's not necessary if they have the same length.
The same length? Not sure. Okay. The one thing is for sure, if you have x is a to some power n and y is some power m, like this, when you concatenate, you will, in both cases, you will get a to the power n plus m. Because, okay, you just pad up some a. So that for sure works. And so for...
Not just an arbitrary word.
What do you mean an arbitrary word?
Any word
to some power.
Any word to some power, right? So basically you replace A with, which is a single letter, by any word U, and you have exactly the same reasoning here. So in this case it will work, and the question is this the only case where it could work? And so here, I might spoil the fun, the answer is yes, and this is the first thing I want to show you, is that concatenation as an operation commutes if and only if your two words X and Y are actually powers of something smaller. So for some palindromes, it's not the case, typically. You might invent palindromes where it's not the case.
ABC and CBA, and it's
ABC, CBA equals CBA, ABC? No? Yes, doesn't work, exactly. And so and this is what you meant by a palindrome. Okay, right. So I think we can recall what the empty word is and what a power is. So first thing I wanted to show is a theorem from the 60s, actually, by Professor Linden and Professor Schutzenberger. I should cite the names, which says that we have the following things are equivalent. First thing is xy equals yx for words x and y. There exists, second thing, there exists an integer n and a word u such that
and an integer m.
yes, actually, x is equals to u to some power m and y is equal to u to some power n. So this is what we just discussed, and you cannot. There is also another way to say it. Is if there exists two other integers, say k and l, such that x to some power k is equal to y to some power l. Third condition. So there are three, we can prove it with three implications. I might leave one or two as an exercise, but let's start it. Maybe like this. So yeah, for the whole lecture, you could pick any alphabet you want. Of course, if you take an alphabet with only a single letter, many things will get less interesting, but it should stay true. But on the blackboard, I will always use alphabet AB, like this. You could do it with more letters if you like. So we remember that it is associative, remember what a power is. All right. I explained how I call the individual letters of a word like this. I explained concatenation. I might need a little bit more vocabulary. I guess everybody knows what a prefix and a suffix is, so I won't define that. But I would need to define a factor. And so a factor is just a subword that is consecutive. So let me write it in a small space here. U factor of W. If U0 UM is equal to WK W, it should be -1 here. K plus M -1. So the letters should really be next to each other. And I call that a factor because the term subword is actually ambiguous. Some people think that a subword is something when you could interspace things between the UI. Here I don't. So I use factor. Can you see why it's called a factor? Because it's a strange word. I should say subword or substring or something like this. So why can I call that a factor?
Probably it has some connection to factorization.
All right. This is true if and only if there exists some P and S such that W is P, U, S.
Probably, yeah.
And give you a hint. Usually when I call something P, it will be a prefix. When I call something S, it will be a suffix. So but that's just meta information. So here you have a factor. A word is a factor of W if and only if you can write W like this. And since we note concatenation as multiplication, this becomes a factor. Of course, P could be the empty word and U would be a prefix. S could be the empty word and U would be a suffix. So this is why we call a factor. And usually when you hear something that sounds familiar from algebra, this means that if you write the equations like this, you will find the common definition we had in algebra. So now we know of what a factor is, what a prefix and a suffix are. So we're ready to prove, let's say, that 1 is equivalent to 2. So once again, if it's not interesting because it's too slow or just plainly not interesting, please tell me because I have other material that I could show. Okay. So, any ideas? Saying equivalence like this. Because there is no especially new concept, it's just plain mathematics, so maybe you already have a few ideas how you would show that.
So now we see that
yes, excuse me, let's say like this.
Prefix of y or y is prefix of
yes.
x, and we can suppose y is prefix of x and write it.
Yeah.
Like that x is equal to y.
All right.
Concatenation.
Yes.
Some other word and then
something will happen. Okay. No, but that's right. That's actually, I will just say one more thing before we explain that. I will say we prove it. We prove 1 implies 2 by induction on the length of xy. You will need that at some point in your what you are going to write. And of course, if xy is something like less than or equal to 1, then you have not much work to do. One of them will be the empty word, so power 0, and the other one will be just one letter to the power 1. Okay, there is nothing to say. So the initialization of the induction poses no problem. And then, okay, by symmetry, up to swapping the roles of x and y, you can write that, I will take my notation. Actually, you can assume that x is not longer than y by symmetry, so without log of generality. So you can write y is equal to x y prime, where I introduce some new y prime. This is what you said, like x is a prefix of y. And then I replace in the initial equation, because that's pretty much the only thing I can do. So I have x y prime, which is equal to x y prime x. Now, of course, I can simplify these x's here. And I have something hopefully strictly shorter. So I can apply the induction hypothesis, because I have something shorter. And I know that x is equal to some u power m, and y prime is equal to some u power n, like this.
But I think in the first place you should say that in case x is empty word.
Yes, that's.
Yeah. Okay.
Yes, okay. You might say that, okay. Yes, in any case, if x is the empty word, you have nothing to say because it's going to be power 0 of something, and the other one can be power 1 or whatever you like. So indeed, if x is the empty word, you have not much work to do for the same reason in the initialization case. And now, in the other case, you do your induction. So by induction hypothesis, you get this. And now you just replace the definition of y is x y prime, which is un, which is indeed another power of. Makes sense? By the way, they are not ready yet, but I prepared rather detailed lecture notes, which are here. So they are too ugly, so I can show them to you now. But if you don't want to take notes, you can still download them later, and it will be even much more detailed and with more material than what we cover here. Hmm?
Great.
And right?
I think that's great. And,
Okay. Right. Okay. So we, like this, we have no pressure if we don't cover all the material, because if you're really interested, we never know, it still exists somewhere. And okay, so this is the kind of reasoning you can do all the time. You just have equations. Like it's pure algebra, actually. You rewrite things, you do inductions, and you prove like this. And so the other way around, if you want to prove 2 implies 1, well, actually, we did it already. This is what we told me. 2 implies 1, we did it, so it's OK. If you're in doubt, you just rewrite. You replace x and y, and you will find something. I can leave the third one as an exercise, because it's really the same style. You will have it in the notes, and it's just OK. We write equations, and so we replace, we rewrite, we do inductions, and so on. But now, why would it be useful, in your opinion, to have, where could we use such a theorem, let's say in computer science, maybe something even practical?
We can store less information if a word is, if we know that about word. If it's power, so I'm not sure.
Yeah, okay, so I think what you're telling me is that this is a way to detect when words are power of something smaller. Indeed, when we have a word that is a power of something smaller, it is usually an interesting situation. It takes less space to store, and for instance, even more things, whatever you might want to do. If you want to look for a substring inside u power n, you feel that you can do it more efficiently than if you don't know that your input is a power. If you look for a substring inside this, you should just look at something circular inside u. Well, you feel that you could design an efficient algorithm. And now we know when 2 things commute. We know actually how to detect sometimes this situation. We know that if 2 words commute, then we will have something, a power of something smaller, and so it's an interesting situation. It makes efficient. Another thing that you might want to use is actually sometimes it's interesting to know when 2 words commute. So there is an example I like. I won't develop it much, but you all used things like Etherpad, I guess, or Google Docs, something where you have a document, text document on a web page. You have several users, and all the users can modify the document, and it updates to everybody. You see what I mean? Okay. These applications, okay, if you want to implement such a thing, you don't have 10,000 solutions. Each user, when you press some key on your keyboard, this is going to send a message to the server, say, insert character B at this position, say. And usually, because of how networks work, you don't send single instruction, you send them by packet. So you can imagine that sigma is the set of all possible instructions. Your documents are of bounded length, so this is a finite alphabet, everything's okay. And each user's computer sends packet of instruction like this, will add such letter, add such letter, add such letter, and so on. But now you're on a network, so maybe user 1 sent packet before user 2, but packet of user 2 arrives first. See what I mean? So you have users sending packet. User 1 sends packet 1, packet being just a sequence of instructions like I was explaining. User 2 sends packet 2, but because the network is not reliable in general, it might happen that server receives packet 2, and only then server receives packet 1. This happens all the time. If you do network programming, you should assume, unless you use some specific protocol that mitigates this, that to users, the time is not preserved. User 1 could send packet first, but be received later. Typically, if user 1 has a very slow internet link, but there might be many more reasons for this. And now, when you're editing your document, this might be a problem because, okay, you know, users are being in conflict and it will make no sense. The things won't be inserted in the right order. And so how do they handle this? They actually try their best so that the packets commute. Like the sequences of instruction have the same effect whatever the order you receive them. So they use this kind of theorem, something more complicated, of course. There are lots of detail that I hide from you, but the very basic thing is they try to make it such that any sequence of instruction commutes with any other sequence of instructions. So whatever you do, it's always commutative to some extent, locally commutative, say. And they use this kind of theorems to ensure that all instructions are actually powers of very elementary instructions. So of course you cannot use only a single one, but using this and a bit of engineering, you can design a protocol for your text editor such that packets might arrive in any order and the result in the end will be the same after some bounded time. So you send your packets, you wait for a few seconds, and you're guaranteed to have something at least stable. And so that's a classical synchronization trick. If all of the things you do commute, then you don't need to synchronize in general. All right. So, everything okay for now? Questions? Should go faster or something? Or it's cool? Just tell me, really.
So far it's okay.
Right. So we discussed before talking about server and so on that the situation when you have a word which is a power of a smaller word, x equals some u to, let me call it r. Let me call it r. R to the n for some integer n, let's say more than or equal to 2. This situation is interesting because, okay, now we can store x with in less space. We can, all things we might want to do to x, we can do them more efficiently. So we should give a name to this situation. And actually, it's going to be a bit different. I will say that in general, so even if n is equal to 1, if I can write this, I will call r a root of x. R is a root of x. So once again, it's a root just because of the usual algebraic thing. X is equal to r squared. Well, r is the root of x, like it should be the square root of x. So in general, r is a root of x, and so in particular, x is a root of itself. This is why I changed it here. Itself. And if x has a root which is not itself, then we say that it, has no roots except itself. Forgot negation here. Then we call x primitive. So actually, the primitive guys are the bad guys. You know, they are primitive. They come from old time, like prehistory. They are very primitive. So we don't like them much. We like words with roots because then we can do more things. So I told you that, okay, maybe we could use this theorem to test if somebody has a root, but this theorem talks about two words. You have an x and a y, so you should, you can test whether they commute or not, and so on. But here, say I have only x and nobody except x. And I want to know whether x is primitive or maybe if it has some smaller root. So maybe you have any idea, I don't know, how may we test whether x is primitive or not? Maybe an algorithm, maybe just an equation?
Probably we can apply the previous theorem and just try splits and splits of x
You want to split x anywhere and test if...
yeah, but this requires n time.
Yes, you should do this n time. Like you have your x, and then you try to split it here, apply this theorem, then you try to split it here, apply this theorem, and so on. Okay, so this would work, but as you noticed, it would require, I think, n square operation if n is the length of x up to some constant. And the way you say it, you probably feel that there is a more efficient way. You look not so sure, so probably you knew that there is some more efficient way. And actually, we can say, so proposition, that x is primitive, no. Yes, okay, let's write it like this. X, let me go, y, okay, w. W is primitive if and only if w is not an internal factor of w square, which is ww. So what I mean by an internal factor is it doesn't occur except as a prefix and as a suffix. Of course, w is a factor of w square because it's a prefix and a suffix. If you have no other copies of w inside here, then w is primitive. And on the contrary, if you have some other copy of w here, then it won't be primitive. So you can try with examples. You write it. You write AB somewhere, just to try it. You write it once again. So this would be my w. W square would be AB. And here I find w in the middle. And just for this reason, I can be sure that w is non-primitive, that it has a smaller root. And if you take something primitive, like ABC, all right, ABC has no smaller root, then you can try, right, ABC, and you find ABC nowhere except at the beginning and at the end as a prefix. So this is what this proposition means. And it's the same kind of proof. I still want to do it. So.
But it's easy to do by
yeah.
the second statement of the theorem.
You mean
This one?
With this? What do you? What should I write?
In case it's not primitive.
Okay.
We have
U is equal to Rn for some n greater or equal than 1. Okay.
Yeah. And
okay.
W to square w is to the power.
Okay, I'm just writing what is obvious, but maybe it's not what you want to say, so just tell me.
But here it's strictly, n is strictly greater than 1.
Yes.
So r to the power of n times 2 is greater than, I see.
Well, here, what
yeah, it's greater than, it's 3 or greater, so we have, yeah.
Just write it. I can make a picture maybe. It would be easier to talk about it.
N is 2 or greater and...
yes, excuse me. Yeah, you mentioned it 3 times, so yes, I write it down. Okay.
And to the power 2 is 4 or greater.
Mm-hmm.
And that's why we have...
yes. The idea is that, of course, we might have even more occurrences of R, but in this case, if W has some root that is non-trivial, you can write like this, maybe with even more occurrences of R, but in any case, you will find W here. So you will find W at a position, so.
It's just because we have 2n occurrences of R, and if we
can just read the first occurrences
and
include the first occurrences in the second one.
All right, so if you want to write this down formally, what you should write at some point is that W occurs at position length of n, which is what I wrote here. You skip the first R letters, and you find another occurrence of W, which is R to the n. So it's written, I mean, the slow way to explain it with all the equations is written in the note, but I think I convinced you enough. But what about the other way around? you suppose that W is the other way around is not much more complicated, but why not? So if W is non-primitive, then it is not an internal, if it's not primitive, sorry, it is an internal factor of W square. And if, on the contrary, say that W is an internal factor of W square, so this is the other way around.
Sorry, may I ask you to try to use bigger letters? Because
Yes, okay, I will. Like this, it's all right?
yeah, fine.
In the worst case, people can refer to the lecture notes. So, internal factor of W square, and you want to show that W has some root which is not itself.
In this case, W consists of concatenated X and Y,
Mm-hmm.
and XY equals YX.
Okay. So you drew, I think you drew a picture in your head. You drew this picture with W, W, and you have some other W inside. And now you decided that you were going to split here, and you will call that X. You will, oh, excuse me. Just, maybe this is not what exactly you decided, but you will call that X. You will call that,
No.
no?
The first notation.
What? You prefer, what notation do you prefer? Okay, you call that X,
Yeah.
you call that Y, and then what?
And then the first W
Is also equal to X, to YX, okay? Because here you have Y. It's more easy on the set to see it on the second one. Here you have Y again, here you have X again, so you have X here
yeah.
and Y here. So you can write it another way around. You can weigh that W.
Why you?
Yes.
That's right, but why did we decide that? Because you say that Y is X concatenated with Y,
Mm-hmm.
but upper you write twice concatenation of Y with X.
Where exactly? First I write that W, I split this W into X and Y, and then I say that since these two things are equal, you have something here. W is an internal factor, so these two things are equal. They are both equal to W squared. So this X must occur here as well, and this Y must occur here as well.
Okay.
You can also write it like with the equation if you prefer, like this. And you can notice that W is prefix of Y. Sorry, Y is a prefix of W. X is a suffix of W. And by a simple computation, you can see that the length of Yx is equal to the length of W. You just simplify. You take the length of both sides, you simplify by W. And so you can realize like this that W is equal to both xy and yx. And then what do? So you have this, and you just apply a theorem here. Don't we forget any detail? Yes. All right. So we apply a theorem here, and to get that x is equal to some root to the power n, y is equal to some root m to the power n, and so w, which is whichever you like, is certainly power n plus m. The slight detail is to notice that y is non-empty and x is non-empty. So this power is not 0 and this power is not 0. And like this you get something that is at least 2, because you have at least 1 here, at least 1 here, and you have at least 2 here. Otherwise you could have n plus m equals to 1 and then that would be primitive, but here it works. So now you have, and this testing exactly this condition is can be done in linear time. Typically, you just, if you're lazy, you just take your test string, you concatenate with itself, and you use your favorite search algorithm to find an occurrence inside. If you really want it to be efficient, you can even use some modulus trick. You can try to search W into W itself with a modulus. Like, instead of actually creating explicitly the concatenation, you can use modulus in the end to emulate somehow concatenation. Like you decide that index, like in this word, position n is equal to position 0. Position n plus 1 is equal to 1. Position n plus 2 is equal to 2. So you can just work with the indices modulo n, and it emulates that you work into a square. So you don't even need to allocate space to do this. But you need to, probably you need to re-implement search algorithm, because the standard library search algorithm doesn't know about modulus, but okay, why not? So okay, so now we're very happy. We have a test for this. The test is efficient, and in case we have a primitive root, I won't show it. Can leave it as an exercise. But with this, we can even find what is the smallest root of all of them, because of course the root, the more interesting it is. So here, with a bit more of work, you can even detect what is the smallest root of W. But I leave that as an exercise. You will see. But yes, so I said the smaller root, like it's unique. It's okay for everybody that if I have two roots of the same length, since they are both prefixes, because a root is a particular case of prefix, if I have two roots of the same length, they are both prefixes of the word, and so they must be equal. But I call that, I think my tongue slipped, and I call that the primitive root. So actually, this is also a remark. Right. And you have a remark. The smallest root of any word is primitive all the time. And it is, so yes, okay, so this, for now it's not very complicated, because if your smallest root were not, actually what I'm saying is that the relation is a root of is transitive. Like if your root has itself a root, like if you have W, it's equal to R to the N, and R is itself equal to T to the M, and of course W is equal to T n times M. And so if you have a root that is itself has a root, then the small root is a root of everybody. So for now I didn't say anything very deep. The interesting thing is that it's if and only if. Like the primitive root is the only one which is the smallest root is the only one which is primitive. Right. So it's the same. I will skip exactly how you write this down. You just write down exactly the same kind of thing we already did. You write down the equations, you work it out, and it comes out that you suppose that the smallest, that you have another primitive root, and then you will end up finding that they are equal. All right. And so like this, you can implement programs. Everything's good so far with the roots? Okay. Right. And so the same comment, this has countless applications, both in text treatment, in algebra, or in whatever you can modelize with words. And that we will see in the second part of the lecture, in the second hour. There are many things you can modelize with words. But okay, for now, I'm still in the same motivation that I want to find interesting words that have good properties for which I can design interesting algorithms and so on. And even if it's not, actually it's even true if you do pure theory. Like usually, simple words with good properties are good for algorithms because you can make more efficient algorithm, and they are good for math because it's usually easier to prove theorems on them. So whatever you job later, you learn to like them. So what else can we have? Like, can we have something else than roots to explain that a word is cool, that we can do things easily with it?
Do you mean quasi-periodic words which you...
No. No, that is ongoing research. I'm not that sadistic. No, but actually a factor of what you just said. Before quasi-periodic. Notice something. I said I didn't call this periodic. I call this root and primitive if it's not, and so on. I didn't say periodic and non-periodic. Why? Because usually the definition of periodic is something like this. I say W is periodic if there exists some K with the right range, such that for all I you have W of I plus K is equal of Wi. You know, you can translate the word and see the same thing. Usually this is how periodicity is defined for general functions and so on. And in general, it has no reason, well, to be equivalent. You have no reason just because, okay, if you have a root, then you're going to be periodic of period length of the root. All right. But the other way around has no reason to be true. You might very well be periodic, but not having a root at all. Can somebody imagine an example?
Yeah, sure. A, B, A.
Right, okay. So this is the pathological one, perfect. So yes, here, this word has period 2. It satisfies this for all the proper indices. And still it has no root, which you can check by yourself. Just to make things, I also may. This one also has no root, if I'm not mistaken, because this A in the end breaks everything, so it has no root, and still it has period 2. And now we have a little accident of definition. So of course, K is called the period. Let me write this differently. Because the definition here are a bit subtle. I say K is a period, sorry for those who are taking note, of W if, so K is a period of W if you have this. And the standard definition of periodic is like W is periodic if it has a period K with K less than or equal to length of W divided by 2. So this is a bit strange. A period is just anything satisfying this. So in particular, in this example, you have period 2, but you're not periodic, technically, because if I want to say that the word is periodic only if it has a period which appears at least twice. Just for the matter that it is weird to say that this word would be periodic if you see nothing twice. You expect to see something several times in a row if you say something is periodic. So usually we want at least this. And it actually makes sense because you can do more things if a word is periodic, like if it has a period smaller than 1/2 of the word. You can also say things in this strange case, but it's another kind of result. And we're going to see both. All right. So now we have the technical one, and then it's going to be cool. So for now, I will forget this special case where you have a period but you're not periodic. I will talk only about periodic words, and so I will say that I will consider period shorter than 1/2 of the word. And as you can see, in this case, you can always decompose W with some period like this, where P prime is a prefix of P. So in particular, this is if and only if you just write the definitions out and you realize it. And in particular, if P prime is the empty word is a prefix of everybody. If P prime is the empty word, we find we are again in the case of having a root. So if you have a root, not yourself, if you have a root and you're not, yes. If you have a root, non-primitive root, then in particular you are periodic. But sometimes you're periodic without a root because you have this P prime arriving here. And now I just made this remark about roots that if you have two roots, then they have a smaller root in common. This is another way to say this. If you have two roots in a word, then they both have a smaller root in common. And this is why in the end the primitive root is unique, the minimum is unique. So it is useful in general to, when you know you have two different roots, you know that these two roots themselves share a smaller root between them. And this is useful information on the structure, in particular if you want to find the smallest root. Here it's a bit the same. One interesting thing we can say about periods is what happens if we know that a word has two different periods. I know that word has period K and I know it has period L. It should have some structure. It is more interesting than just having one period. It should say things. So.
In this case, they share the same root?
It's not clear that they have roots at all, because periods have no reason to be...
Periods have the same root.
I'm not sure. In general.
One period is divisible by another.
You sure?
No.
Because about the root, I'm not sure, to be honest. I think that you could invent pathological cases where you make the root thing fail. Because you can always stick these prefixes in. But what I had in mind is more something about, yes, one period is divisible by another. Not exactly, but that's more on the way. There is something to show in this direction. Actually, you can make a mix of both your ideas. Try. They would have a smaller period that is both divides the first one and the second one.
Doesn't that mean that this period is of both of them?
It's a period of both of them. It depends because sometimes you have if you have two periods P1 and P2, it might be that P2 divides P1. And so P2 divides itself, okay, but it's you should be careful in corner cases, say. So let me write it formally, what I have. So if I have a word W, so this is a theorem by Fine and Wilf. Once again, something not complicated to show, but celebrated because you have to ask yourself the question, actually. And once you know it, it's interesting. So, let W denote a word and say with two periods. And just not to confuse myself, I will use the same as here. P and Q. If W is long enough, and long enough means this, then the greatest common divisor is also a period. That's what you can say in full generality. If you want to say something more about who divises who, about the roots and so on, I strongly suspect that you need other conditions on P and Q to avoid strange corner cases. And so we can prove this, and that would be slightly, I think, less trivial than the beginning. So everybody is with me for now? Okay. So let's try to prove it. So first, I will need some strange notation because it will make things practical. If I have an integer n, I will note n bar like this, the prefix of length. I will note n bar exactly this word actually. N bar is w0, w1, w n minus 1. So n bar is the prefix of length n in w. So the bar depends on w, but we have only one w, so it won't be ambiguous. And so like this, I can freely talk about integer or about prefixes of exactly this length, and it will make things easier. And, okay, as usual, we make recurrence, like we reason by induction on P plus Q. You see a bit the same pattern as we had in the first Lindon-Chilson-Berger theorem. So we reason by induction P plus Q, and let me check exactly. Yes, okay, so we will need to talk about the greatest common divisor all the time, so I'm going to give it a name. Yes, this is what I missed. Something's wrong here. So if P plus Q is smaller or equal to G, then you have nothing to do. Basically what I mean is that if already one period is a multiple of the other, then you have nothing to prove, because it's a self-referential statement, more or less. Like basically, if you prefer.
The one about possibilities, P is empty or Q is empty.
Yes.
Yeah.
Or, but even more generally, if P equals G, which is less than Q, then you have nothing to do either. This is what I mean, actually, by P plus Q. It's an algebraic trick just to write this. So now, well, you should suppose something else. So by symmetry, just without loss of generality, yes, we can suppose that all the time we can suppose that P is larger than Q, just because otherwise you rename them. And so in this case, this means that if Q is exactly is already a divisor of if Q is already a divisor of P, I have nothing to say. In particular, if Q is the greatest common divisor, is the smallest divisor of P, then or the largest one, well, you got it. I'm getting a bit lost in this base case. So otherwise, what happens? And it's the same. I asked the question because it's the same. P is larger than Q. This means that Q is a prefix of P. Just because I rewrite exactly this, actually. And no. P minus G. Yes, okay. And I will give a name. Hello. Consider U equal. I'm sorry, there is something unclear in what I prepared, so I need to improvise a little bit. P minus G.
Are you going to use a linear?
I'm going to use linear what?
I thought about
Linear?
We can, there exists such x and y that g is equal to pi times
Yeah,
x plus-
you mean Euclidean division? This is how it's called. Yes. Yes, at some point it will. But I just need to get, this is actually the trick. I just need to get the details right if I want to write it formally, but this is basically the trick. I will perform Euclidean division. Euclid is everywhere, you have no idea. All right, and so now I can write, because the word is long enough, I can write, no, come back. Okay, it's completely dead now. This is not completely trivial to get right. This is why I wanted to be really careful, but we can write ui equals wi, just because it is a prefix, which is equal to wi plus p, because p is a period and the word is long enough, so we're safe, which is also equal to wi plus p minus g minus q, sorry. I cannot use recurrence hypothesis yet. And this is back in u because it is short enough, so we have p minus q as also a period of u. I'm pretty sure something wrong slipped in. This is why I'm extremely cautious since 5 minutes, so if you see something strange, please tell me. But okay. So, of course, U has periods. So now, U has periods. Q, because Q is smaller than this, and G, and P minus Q, sorry. So by recurrence hypothesis, it has period GCD of these two things. Minus Q, sorry. Which by Euclid is the same as this. And now it gets this is where you perform your integer division, your Euclidean division actually. So Q is a prefix of U. So it also has these periods. G.
What do we denote by HR?
Hypothesis of recurrence.
Of induction.
Induction, if you prefer. Okay, sorry, this is French language kicking in sometimes. Like this. And it should even probably be AH for that matter, but I might do this mistake quite a lot. So it has period G, and G divides Q. So actually it's even stronger than this, since G is a divisor of the length of Q bar, sorry. So G divides Q by definition. So you can write Q is equal to G to some power, enough mix up, M this time. Is it all right? I'm making sense? Okay.
Why it has a period G?
Because this is G. Like Q is a U. I showed that U has periods P and P minus Q. Then I applied recurrence induction hypothesis. I got that U has this this period by induction hypothesis. And now Q is shorter than U actually. So since U is a prefix and Q bar technically is a prefix, they share the same period. And because G is the greatest common divisor, it divides the integer Q, so we can write it like this. So this is where I start to do what you suggested. I divide things and so on. And since Q is a period, Q itself is a period of W. That was our initial. So we can write W is equal to some power of G with G prime, and yes, let's call it N. Doesn't matter that much. No, not exactly. What did I write wrong here? Q is a period of U. We cannot write that directly because this G prime here might misalign. So let me take that back. I can write Q to the N Q prime. That's for, and that's safe because I just said that Q is a period of W. But I expanded the definition. And now I can rewrite, if you want. Since I wrote this, I can rewrite this as G power M power N with, and this is a prefix of Q, so it also has period G times G power K J prime. And now you can factor out and get what you want if you insist on being precise. So the core idea, maybe the technicalities are a bit dirty, but the core idea is that first you consider a prefix of this length. You can deduce that it has this prefix has this period just by writing equalities you have in your hypothesis. You apply induction hypothesis and you know that this smaller prefix has period G, but since G is the greatest common divisor, it divides the length of Q, so you can rewrite everything and get this in the end. And the interesting thing is that it works. I might fail to make this appear very clearly, but it works exactly like the Euclid division. It works exactly like when you need to prove that there exists a unique pair of Q and P and Q integers such that the division works. So the real technical thing is written down in the notes. But the main idea is this. All right, I think we're getting towards the end of the first term. At what time are we supposed to end?
Yeah, now it's time of break, and the next class starts at 12:10.
All right. Okay. In this case, I will stop here for the break. I might just mention what other thing that could have been covered, like if we had 10 more minutes, but I will just mention it very quickly.
Long breaks.
No, but yeah, it's cool to have long breaks. I like long breaks. Yes, it's not long enough, but okay. I'm also here to teach. But just to mention quickly, and you will find in notes, we also study the notion of words. Something of interest is the notion of words being rotation of each other. So it still comes from the Linden-Schuizenberger theorem. Something else is that we say if we have two words, u is equal to xy and v is equal to yx, this means that u and v are a rotation of each other. And we call that being conjugate. And you can also say things about words being conjugate. There is also a theory and a few basic results that I could have covered about under which condition two words are conjugate or not, and what can it bring to you to know that two words are conjugate. And just to mention in particular, you remember at some point I told you about working with indices modulo n. Like when we had this algorithm to find the primitive root or something, I told you, instead of concatenating, just take indices modulo n. Actually, this is very common. In many applications, you don't consider words, you consider circular words, where basically you consider indices modulo n. And this means that two words which are rotation of each other are considered equivalent. But of course, when you implement things in a machine, you have character strings, and working with indices modulo n everywhere is a bit subtle sometimes, and you have useful result to work with conjugates of word efficiently, to choose among all the rotation of a possible one, to choose one of them which is distinguished, like a representative of the equivalence class. And okay, so there are material cover, but I won't have time even in 10 minutes, just to mention that it's important. So let's have a break, and after the break we discuss infinite words, so we won't have a big enough whiteboard, and the problem of Hanoi towers.